Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. And we're in chapter 1 part of this playlist, which I'm calling Probability. And let's jump to today's topic, which is the multinomial coefficient. Now, this is part of the section Counting Methods. And so, really, I think of the multinomial coefficient in two different ways in regards to counting things. So, one, the number of combinations of indistinct objects divided into k different groups in such a way that j equals 1 to k, the jth group contains exactly nj elements, where n is the sum of the number of elements in each of the different groups. So that's one way to think about it. Also, the number of combinations of n objects with k different types. Now assume nj objects of type j for j equals 1 to k, where n is equal to the sum of these nj's. The general formula is this right here. It's n factorial divided by n1 factorial times n2 factorial all the way to nk factorial. And let's go through several examples using this formula. First, let's suppose that a club consists of 20 members and must be divided into 3 committees, A, B, and C. Committees A and B must have 8 members, and C must have 4 members. How many ways can club members be assigned to these committees? Well, this is example 1, but the first way to think about this multinomial coefficient. You have 20 distinct members and you're separating them into 3 groups. And so this is it. It's 20 factorial divided by 8 factorial times 8 factorial times 4 factorial. And so there's over 62 million ways to sort these 20 members into these 3 committees. Now example 2, suppose that 12 dice are to be rolled. What is the probability that 6 different numbers appear twice? And so this is actually an example of the second way to think about this multinomial coefficient. So we have 12 dice, but there's only 6 ways to roll it. There's 6 different types of, and so here, since we want probability, we're going to look at the number of ways to roll 12 dice and have 2 numbers of each. So 2 1s, 2 2s, 2 3s, all the way to 2 6s. And then we're going to divide it by the total number of ways to roll 6 dice. So if we do that one first, the denominator, that's the divide by here, 6 to the 12, right? Each die has 6 different ways or 6 different outcomes, and there's 12 dice, so it's 6 to the 12. Now the number of ways to roll 12 dice and have 2 numbers of each show up is 12 factorial divided by 2 factorial, times 2 factorial times 2 factorial 6 times, or 2 factorial to the 6th, which then when you crunch the numbers, it's this 0.0034. Now this second problem or example, we're going to solve it in 2 different ways. So a deck of 52 cards contains 13 hearts. Now suppose that the cards are shuffled and distributed among 4 players, A, B, C, and D, so that each player receives 13 cards. Now what is the probability that player A receives 6 hearts, player B receives 4 hearts, player C receives 2 hearts, and player D receives 1 hearts? And now there's 2 different solutions. So the first one is the total number of elements in the sample space. So the total number of ways to deal 52 distinct cards into 4 groups. So it's 52 factorial divided by 13 factorial raised to the 4th, right? Because each of the 4 groups is 13 factorial. So that's the easy part. So next, we're going to think about um, how many ways we can deal the hearts in the correct way, and then how many ways we can deal the non-hearts in correct ways, and then multiply. We're going to use the multiplication rule. So the number of ways to deal each player the correct number of hearts is 13 factorial divided by 6 factorial, 4 factorial, 2 factorial, 1 factorial. But that's just distributing the hearts. Now, even if we don't move the hearts around, we can change the non-heart cards and it creates more combinations. So we need to figure out how many ways to deal the remaining 39 cards so that each player receives 13 cards. So the answer is 39 factorial divided by 7 factorial. Now it's 7 because we dealt them 6 hearts. We need 7 more cards. And then it's 9 factorial. That's because we dealt, player B needs 4 hearts and 9 non-hearts. And then it's 11 factorial and 12 factorial. So that's the number, whatever it is. It's a big one. So the required probability is the product of the number of ways to deal the hearts correctly, the number of ways to deal the non-hearts correctly so that their cards, they each have 13 cards, divided by the total number of ways to deal 52 cards into 4 groups, each having 13. Then you can invert and multiply, and then multiply that out, and you get 0.00196. So the second way to think about this, and I'm not for sure which of these solutions I like better, but both are so informative on how to calculate these probabilities. So think of a deck as having 52 positions, right? Position 1, position 2, all the way to position 52. Now note that the 13 hearts occupy 13 of these positions. Also note that 13 of the cards or positions are assigned to player A when the cards are dealt. Okay, so if you think about that, you shuffle the deck and now you get ready to deal. Player A's cards are already determined. So you deal one to player A, and then B, C, D, and then the next one goes to A, B, C, D, A. So we know player A's cards. And then similarly, these for players B, C, and D, they also have 13 cards slash positions in the deck assigned to them. And there's no overlap. Player A has their cards, player B has their cards, C and D also have their cards. Now, player A must have 6 hearts in their cards, right? Because we're trying to find the probability that player A has 6 hearts, player B has 4, C has 2, and D has 1. So put 6 hearts in their positions. And players, B and C and D must have 4 hearts, 2 hearts, and 1 hearts in their respective cards or their positions in that deck. So now the required probability is this. So for player B, they have 13 cards, and we need to choose 6 of those positions to be hearts. So it's 13 choose 6. That's the number of ways we can mix up player A's cards so they have 6 hearts. Player B, we have to put 4 hearts in their 13 cards, but we have to do it randomly. How many ways can we do it? That's 13 choose 4. Player C, 13 choose 2. Player D is 13 choose 1. Now the denominator, the total number of ways to mix up the deck is, remember, we have 52 cards and 13 spots will be filled with the hearts. So how many ways can we put those 13 cards in a deck of 52? So it's 52 choose 13. And if we calculate that probability, it's 0.00196, which is the same as that we achieved in the first solution. Okay, so those are the just two different ways to think about the same problem. Well, it's 10 minutes. I'm going to call this video complete. I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.